The goal of this experiment was to measure the speed of sound waves using sonar and to observe a relationship between the speed of sound and both altitude and temperature. We were able to find a mathematical model that showed that speed of sound already had a dependence on temperature. This is shown by equation 1 on the right side of the screen. We expected to observe a similar relationship in the data we collected and wanted to see if there was any dependence on altitude. We measured the speed of sound by utilizing the capabilities of an ultrasonic sensor. Additionally, for each measurement of the speed of sound, we also collected measurements of the altitude and temperature the speed of sound measurement was taken at using a barometric pressure, altitude, temperature sensor. Team members were each tasked with taking measurements at multiple different temperatures and, if possible, at different altitudes. The speed of sound has been seen to fluctuate dramatically, dependent on the characteristics of the current environments. Devices that utilize sound waves to take measurements are potentially restricted by this uncertainty in which the speed of the sound wave propagates. The creation of a model or device that accurately and quickly measures the speed of sound based on the environment's current conditions would be useful in devices such as sonar probes that are used to measure the position and velocity of an object using sound waves.
The two main sensors used in this project were the MPL sensor used to measure temperature and altitude, and the HCSR04 sensor used to measure speed of sound. The MPL sensor uses a barometer to measure pressure, then uses this equation to give altitude in meters. The expected experimental range for our experiment was 300 to 2,000 meters for altitude, and 4 to 45 degrees Celsius for temperature, both of which fall within the sensor's operating range. The MPL also came with a pre-built library that made it much easier to collect data. The HC ultrasonic sensor operates on 5 volts and has an effective range of 2 to 400 centimeters, which fits our experimental range of 10 centimeters. It has a speaker and a microphone, which together allow us to know how long it takes the sound wave to travel a set distance of 20 centimeters.
Now, I'll talk about how our device collects data. First, the ultrasonic sensor uses TTL protocol to send and receive data. The sensor receives a trigger pulse, then immediately emits a sound wave. When the sensor hears the echo of this sound wave, it returns an echo pulse that represents the amount of time it took to receive the sound wave. Next, the UNO controller board reads the current I2C analog output from the altimeter and temperature sensor. The controller takes data 100 times, then reports and records the average of each value to the SD card.
The expected speed of sound was calculated for each recorded temperature using the mathematical model. The expected speed of sound at each altitude was calculated based off the temperature recorded at that altitude. Each altitude measurement was predicted with a map-based elevation finding tool.
For our design process, we chose to place the ultrasonic sensor 10 centimeters away from a reflector board because this was a distance that was within the operable range, and it was also a nice distance to fit the setup within a portable box. And we fit all of our components in a box because we plan on moving to many locations to collect data. And here is a general setup for each lab member. And for our calculations, we found the speed of sound by dividing 20 centimeters by the time at which the signal was sent out and received by the ultrasonic sensor. And we did this about 100 times in one run. We also measured altitude and temperature 100 times and averaged those values at the end of a for loop. For our design process, it was pretty simple. Once we found a nice location, a flat surface, we just pressed the reset button and let the program run through. And for our project, we traveled to our local mountains to get a nice range of altitudes, and we traveled to our freezers and ovens to get a nice range of temperatures.
After running trials, we plotted each member's data against the expected data. We quickly realized our data tended to cluster around specific speed of sound values due to differences in our setup. To fix this, each member took a calibration measurement at 21 degrees Celsius and compared that to the expected value, applying the difference as an offset to the rest of that member's data. This is the calibrated altitude graph. The speed of sound measurements are very scattered, and there appears to be no clear positive or negative correlation. This would imply that speed of sound is not dependent directly on altitude, a fact verified by the lack of an altitude term in our mathematical model. In our temperature graph, there's a strong cluster of data points in room temperature ranges and not much data in outer temperatures. Despite that, the overall trend line closely matches the expected trend line given by our equation. This seems to support the model as an accurate method of determining speed of sound based on temperature.
Our group identified several areas during our project for future work. First, because the speed of sound is very large compared to the size of our devices, small errors in measuring the distance from the sensor to the reflecting surface result in much larger errors in the reported speed of sound. Future designs could use a larger distance to measure the speed of sound and more accurately measure the distance to the reflecting surface. Future semesters of E80 could also add additional sensors to investigate other factors of the speed of sound, particularly those affecting the speed of sound underwater.